Okay, hello everyone. Welcome to our Physics 8-hour Notes Unit 3 lecture. My name is Alicia. Today I'm going to be taking you guys through some of the content for Unit 3 of Physics, and then I'm also going to be taking you through some of the tips and advice that I have for you guys as somebody who recently graduated and kind of got through physics and juggled a lot of other difficult subjects as well. And I'm going to be explaining all the concepts to you guys in hopefully a way that is really understandable, kind of from a student's perspective. So, before we get into an overview of what we're going to be doing today, I'll really quickly mention that today's lecture is provided by 8-hour Notes. So 8-hour Notes provides free resources for students, including study guides, lectures, discussions, videos, newsletters, the 8-hour calculator, articles, and heaps more. 8-hour Notes also provides tutoring from recent graduates, study guides with revision materials, and Ed Unlimited, which includes all of the resources for all of your subjects in one space. And then with a special thanks to our sponsors, let's get into an overview of what we're doing today. So, really quickly, the structure of our lecture today, under the announcements heading, is going to be a 2-hour lecture with 2 main blocks of content. If you guys have any questions at any point, ask using the live chat below. If you see a question that's similar to yours, please just upvote that so we don't have multiple questions kind of the same nature. And if you're looking for any extra resources or anything, I'll show you a few great places throughout the lecture. But yeah, if you have any questions about anything at all, if there's a question, an example that we've just gone through that you don't understand, a concept that you didn't quite get in class, or even a concept that we haven't learnt yet, or not doing in the lecture, but you just wanted some extra clarification on. If you have any questions about study skills, managing all of your subjects, anything like that, please ask. As I said, I recently graduated as well, so I kind of have an arsenal of things that I did to kind of get through and get the best possible marks. Also, if you have any questions about like uni, which uni you want to go to, what degree you want to choose, moving out of home, colleges, anything like that, feel free to also ask those. So, getting into the content that we're actually going to be covering today. So we're going to be going over a review of Unit 3. So we're going to be going over gravity and motion and electromagnetism. And then we're also going to be going over an overview of Unit 4 content. So that's going to include special relativity, quantum theory, and the standard model. So this stuff is going to be like a kind of a little bit of a taste of what you guys are going to get to in the future. So after that, we're going to go over some study tips and more of a final reflection. And yeah, that's what we're going to go over today. So before we get into the content, I'll go over a quick overview of just a little bit about myself. So I graduated from Boona State High School in 2021, so a little bit over a year and a bit ago. I got an ATAR of 99.55, and I also think the majority of that ATAR was because I did well in all of my STEM subjects, which scaled really well, of course. So So the subjects that I did were physics, of course, and then methods, specialist, and then English and philosophy and reason. Um, so I definitely I didn't do kind of the like all of the most difficult subjects, like some people do, with biology and chemistry too. But I still managed to get a pretty high ATAR. So the degree that I'm currently studying is in law and economics at UQ. So if you have any questions about my degree, law in particular, I guess, or UQ or anything, please feel free to ask those in the chat. Um, the hobbies that I have kind of involve reading, bushwalking, and sewing. Um, maybe sound a little bit lame, but they're really fun. Scaly things. So, yeah, if you have any personal questions or anything, feel free to ask. But yeah, now let's get into some of the content. So, starting off with a review of gravity and motion. So, this is the syllabus link for the first kind of topic, which is vectors. So we need to use vector analysis to resolve a vector into two perpendicular components. And then we need to solve vector problems by resolving vectors into components, adding or subtracting the components, and recombining them to determine the resultant vector. So we're going to go over how to do these steps now, but something you should keep in mind if you're kind of going, oh, vectors are easy, kind of rolling your eyes a little bit, is this content actually becomes very important. I mean, of course, in projectile motion, which you've probably touched on, but also in electromagnetism. The vector analysis is actually really important in electromagnetism, and it gets into more complex vector analysis, kind of involving all of the trigonometry rules like the sine and cosine rule. So my point is, it is actually really important to understand this stuff, and to work on it a little bit instead of just kind of like shrugging it off. Because I know that's what I did in year 12. And then when I got to electromagnetism a little bit, I was like, ooh, what does this even mean? Okay, so resolving vectors into components, as you can see here in our diagram, requires the use of our trig ratios, our sine, cos, and tan, which hopefully you guys remember from your math subjects. So, our vector, of course, forms a right angle triangle with the adjacent and opposite, or rather with the x and y components. So that's why we can use our trig rules. So what this basically tells us is that the x component is going to be equal to the hypotenuse multiplied by the cos of the direction, or so on, applying these rules. The other law that you can use to apply to resolve vectors into components is Pythagoras, where of course you need to let the hypotenuse equal one side and then the opposite and the adjacent squared on the other side. Okay, now getting into a little bit more of what a vector is. So vectors have both a magnitude and a direction. So a lot of the quantities that maybe you've worked with up until this point will just have a magnitude, such as 5 kilometers, 3 kilograms, 3 meters per second, stuff like that. However, a vector has both magnitude and direction. So it will be 3 meters south, 5 meters per second to the left, um, 3 meters per second at an angle of 30 degrees. They all include directions. So our vectors can be resolved into components, and to resolve with these vectors, we need to resolve them into components using our trig, and then add and subtract these components, and then find the vector sum. So I won't go over a too in-depth example of this, just because we are going to get into applications of these in our next topics. But really quickly, what these steps are kind of describing is if you have, say, two vectors like this, and you wanted to add them to find the resultant vector, this green one here, what you would need to do is you would need to find the horizontal and vertical components of each, and then add the horizontal components, because of course that's going to give you the total horizontal component, and then add the vertical components. So we're going to get into a few examples of that in a second, but that's basically what these few steps are describing. Okay, so now we're getting onto kind of the applications of what we're going to use vectors. So the first one is in projectile motion, and the second is with inclined planes. So when we're working with projectile motion, we need to apply vector analysis to determine the horizontal and vertical components, and then from there solve problems. So we're going to get onto projectile motion now. So when we work with 2D motion, we need to resolve our vectors, including velocity, acceleration, and displacement, and apply our 1D kinematic formulas to each dimension individually. So, situations where acceleration is constant can be described by these formulas here. So remember, projectile motion is a case where our acceleration is constant, because the only acceleration that we're considering is acceleration due to gravity, which is always 9.8 meters per second towards the ground. So because our acceleration is constant, we can apply these formulas. Now, of course, remember there is the other factor of air resistance. However, in year 12, we don't consider air resistance. So even though air resistance is like an acceleration factor, because it would be slowing the projectile down, we can kind of assume that it's negligible because it's going to be so small. And then we can also describe the average velocity and acceleration with these formulas. I'll just quickly give you guys an overview of what projectile motion looks like, and some important things to kind of pop in your notes. Remember that the maximum height of a projectile occurs when the velocity in the y direction is equal to 0. Remember that the horizontal velocity is going to be constant because there's no acceleration acting in the horizontal direction. There's only acceleration acting downwards or vertically. So there's going to be acceleration vertically but not horizontally. Remember, the reason why the maximum height occurs at Vy equals 0 is because the projectile is decelerating, or it's getting slower and slower when it's moving upwards because the force of gravity is acting against it. So it is going to be, it's going to have the largest vertical component at the beginning here, and then it's going to slow down, and at a certain point it's going to stop going up and start going down, and that is when it's going to turn around, and its velocity in the y direction is now going to be negative because it's falling downwards. So it's positive, 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 but it's getting smaller and smaller and smaller. Now it's negative, negative, negative. So that's why that occurs. Okay, now we're going to get onto an overview of circular motion. So remember, we are describing uniform circular motion. We're going to be going over the concepts of average speed and period. And then we're going to solve problems using the formulas in our formula sheet, and also go over the terms centripetal acceleration and centripetal force. So one tip that I have for you guys, just as you're kind of maybe making notes in preparation for your external, because I know you guys, you don't have any internal exams, but you need to be preparing for your externals. Something that I'd recommend, especially for physics and also other sciences, although I didn't do them, I imagine that this would also help. For kind of syllabus dot points like this, where we need to define centripetal acceleration and centripetal force, it's really useful to make notes or flashcards of the QCEE definitions of these two terms. And the reason for that is, in your external, you're going to have 20 multiple choice questions, and a decent amount of those multiple choice questions are going to be on like definitions. They're just going to say like, oh, like what's the definition of this term? And they're going to give you like 4 different options, and you need to pick one. The correct one is always going to be the QCEE definition, the official one. So if you memorize those throughout the year, those easy 20 marks on the multiple choice are going to be no-brainers for you. So the reason that it's important to memorize these is because they'll often try to trick you up and kind of change a few words around. So if you don't know the QCEE definition, you'll spend too long kind of going through the options and thinking about them. It's way more efficient to just know the terms before you go into the exam, so you can spend that time going through the other, like the short response and long response. If you're looking for where to find the QCEE definitions, all you need to do is go onto the syllabus, the big PDF document, and then Control F, like search the document for the term. So I'd Control F centripetal acceleration, and then go down until the end of the document where the glossary is, and then find that definition and just copy paste it into your notes. Absolutely saved me. Brilliant tip. The other thing, which I will get into when we get into more of the electromagnetism topic, is how you can actually remember like the explain syllabus dot points. We'll get into that later. Okay, so getting onto our centripetal acceleration, our circular motion, don't know what I'm saying. So when a force acts to constantly change the motion of an object, then the object will follow a circular path. So, the net force in circular motion is always directed inwards. And this is kind of, before we get into the other elements of circular motion, I'll just explain one thing to you guys, which is kind of a common misunderstanding with circular motion. And that is that, like, a misunderstanding of, like, why the force is acting inwards and the acceleration is acting inwards. Like, how are you accelerating inwards towards the center of motion if you're kind of moving in a different direction? So, one way to think about this is, of course, that if you're moving at a certain velocity, you're being kind of, there's like a force holding you to the center of motion. So you want to move off, but there's a force holding you there. So think about perhaps a ball on a string that you're kind of whirling around in a circle. The ball itself at every point wants to move away in the exact same direction that it is traveling in at that moment, right? It's one of Newton's laws. The object will always want to travel in the way that it's going at that moment unless acted on by another force. So in the ball's case, the string in the center is holding it and forcing it to go around in this direction. So it's always actually accelerating inwards because it's always kind of being pulled back towards the center of motion. Another thing to think about with circular motion is, of course, I think the misunderstanding about why, when you're experiencing circular motion, you feel like you're being pulled away from the center of motion. This is something that I remember when my teacher told me in year 12. I absolutely did not believe him. He said, no, 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 the force acts towards the center of motion. And I said, I do not believe you. But it makes a lot of intuitive sense if you think about it really hard. And mind you, it took me a couple of months to finally understand this. So imagine that you are driving, right? You're just driving along a road, a straight little road, and you brake. You brake really hard. I don't know, maybe you see something, there's a cute little bird walking across the road, you brake really hard, and you feel yourself being like thrown forward into the front, into the steering wheel, right? Which makes sense. So even though the car itself is slowing down, your body kind of acts in the opposite direction because it wants to continue in the motion that it had before. Previously, it was going like 100 k's an hour, but now it's slowed to nothing, and your body wants to keep moving at 100 k's an hour, but it's been acted on this force which has now stopped it from moving like that. So it's going to continue and like move forward. It's inertia, right? Your body has mass, so it takes energy to move it. So thinking about this in the context of circular motion, if you are driving around a roundabout, or I don't know, you're doing a donut or something, but driving around a roundabout is probably safer. If you're driving around a roundabout, you feel like, I mean, if you're going fast enough, you feel like you're being pulled away from the center of motion. But that's because the force is pulling you inwards, but your body is resisting that change because it has inertia. I hope that finally makes sense for you guys. If you still don't understand the concept, please put a question in the live chat and I'll answer it. But now that the conceptual stuff is out of the way, let's get into more of the formula specific stuff. So, as you can see here, the real force underlies a theoretical centripetal force that causes centripetal acceleration and a change in velocity. Remember, the velocity is changing. However, the only reason the velocity is changing is because the direction at which the ball is moving or the object is moving is constantly changing, but its speed is not changing. So the velocity changes in direction, but not magnitude. The ball is moving at a constant speed, but it's changing direction. The average speed of the object is going to be given by distance over time. The distance is, of course, going to be the circumference of the kind of this circle that we're considering, which is going to be 2 pi r, circumference is 2 pi r, divided by time. The acceleration is going to be given by velocity squared divided by the radius, which is going to be equal to 4 times pi squared times the radius divided by the period. And then the force, the net force, is going to be equal to mass times acceleration, or 4 pi squared r times m divided by the period squared. So all of these formulas are in your formula book. It's kind of a case of practicing, applying them, and just kind of having a basic understanding of the concept. So, quick question, have a quick think about the definition of normal force. Chuck your answer in the live chat below. If you need a moment to think, pause the recording. But the answer is going to be what I pop in the live chat below. Oh, and I just showed it there. The normal force is the force acting along an imaginary line perpendicular to the surface. So for our surfaces here, the normal force is going to be acting at right angles. That definition is the QCEE official definition. So this is the kind of thing that you would want to memorize for your external. So, getting into gravitational force and fields. So this is the syllabus requirements for gravitational force and field. You need to understand Newton's law of universal gravitation, solve problems, and define gravitational fields. So, gravity is the attractive force that two masses experience between each other. And Newton's law of universal gravitation describes quantitatively the equal gravitational forces acting between two bodies based on their mass and the distance between them. So what this tells us is that, and this equation is on your formula sheet too, what this tells us is that our force of gravity is going to be greater if the masses are greater, which makes sense. If you have, like the sun is going to have more gravity than like a paperclip. However, the force experienced by the two bodies is going to decrease as they get farther apart, which also makes sense. And then our big G here is our gravitational constant, which is a number which is written in your formula book, so you don't need to remember it. The other important thing about this slide is to remember that the forces experienced by the two masses are going to be equal. So even though this blue mass here is bigger than this green mass, the forces exerted on both of them are going to be equal. So have a quick think about why that might be. Pause the recording if you need to. But the reason that the force exerted by both bodies is going to be the same regardless of their mass is because, remember one of Newton's laws, every force has an equal and opposite force. So, or every action has an equal and opposite reaction. So what this means is that the forces exerted by the two masses are going to have the same magnitude. However, the effect is going to be different because of the law of inertia. So the force exerted by the two masses is going to be the same. However, this mass is going to kind of feel more of an effect because it's smaller, so it requires less energy to move. And this mass is going to feel less force than that. It's going to move not as much because it is larger, so it requires more energy to move. Okay. So now getting onto gravitational field strength. So we've seen that gravitational fields exert a force on masses within them, and that the force is dependent on the object's mass. We can define the gravitational field strength, G, as the amount of gravitational force per unit mass. So on Earth, our G is 9.8 newtons per kilogram. However, of course, the gravitational field strength is going to be different at different areas. So the gravitational field strength, as you might know, on the moon is a lot less because the moon is a lot smaller, so it has a lot less gravity. This is the formula that you will need to use to determine the gravitational field strength. And the force on an object, given the gravitational field strength, is going to therefore be equal to G multiplied by the two masses divided by R squared. So this tells us the strength of the gravitational field, the 9.8 meters per second squared. That's the acceleration, the 9.8 newtons per kilogram. And this one tells us the force that an object is going to experience as a result of that gravitational field strength. So of course, the force is going to be in newtons. So, getting onto orbits. So for orbits, you need to recall Kepler's laws of planetary motion. You need to solve problems involving Kepler's third law. And you need to recall that Kepler's third law can be derived from the relationship between Newton's law of universal gravitation and uniform circular motion. So, for recalling Kepler's laws, what I'd recommend is again going to the QCEE official definitions and memorizing those just so you don't get mixed up with anything. So as we can see here, when we're talking about orbits, gravity is always going to be directed inwards towards the mass body, because remember we are talking about circular motion in a sense, or the orbital motion. If an object is moving perpendicular to this force at a velocity equal to the velocity the curved surface of the planet moves away from it, then the mass will fall away from it at the exact same rate as it falls towards it. So, what this tells us is that gravity acts constantly to change the velocity direction of the satellite. Okay, so moving on to the law of ellipses, and this is one of Kepler's laws. So the law is that all planets move in an elliptical orbit around the sun, with the sun as one of the foci. So all of these maths down here, you don't need to know, but it is good to understand. Remember, an ellipsis is a kind of like an oval shape. And there are going to be two foci, one here and one here. So, as you can see, the sun is going to be one of the foci, and the planet is going to move in an orbit around, with the sun as one of the foci. The law of equal areas tells us that in any given equal time periods, the area of the ellipsis that the planet orbits covers will be the same. So what this tells us is that if these two shaded areas are equal, because there is like a greater distance to cover here than over here, there's a greater distance to cover here, but this has to be done in the same amount of time as Q to P. So the planet needs to move faster when it's closer to the focal point and move slower when it's further away. Okay, and this is because as a satellite moves towards the body that it's orbiting, the gravitational field strength and thus force acting on it increase. And as such, its velocity increases because there's more force acting on it. Okay. The law of harmonies, and this is just the third law, and as you can see, it is the equation that you are given in your formula sheet. And it tells us that the square of the period of any planet's orbit is proportional to the cube of the semi-major axis to its orbit. So you don't actually need to remember the definition in words, because this formula is given to you in the formula sheet. So the T is the period in years or seconds. G is the gravitational constant. M is the central mass, the mass around which the satellite is orbiting. And A is going to be the distance semi-major axis. Or in other words, the radius. So, we don't need to go through this. So, getting on to our review of electromagnetism. So, we're going to be going back over electrostatics. So remember, electrostatics involves charged particles which create an electric field and influence one another due to their charges. The reason that we call these electrostatics is because the charges are staying stationary, stationary electrostatics. However, when we get into magnetism, the charges are going to be moving. And because the charges are moving, they're generating a magnetic field. So, when we're talking about electrostatics, we're talking about the force generated by the particles due to their charge. So, to calculate the force on two charges due to their electric field, we need to use Coulomb's law, which is in your formula sheet. It tells us that the force between the two charges is going to be equal to Coulomb's constant, and that number is in your formula sheet as well, multiplied by the two charges themselves in coulombs and divided by the distance between them. So what this tells us is that a greater force is going to be exerted if the charge on the two particles is greater, and the greater force is going to be exerted if the particles themselves are closer to one another. Again, similarly to with Newton's laws and gravity, the force acting on the two objects is going to be equal. Because remember, applying Newton's laws, every action has an equal and opposite reaction. So even if the two particles themselves have different charges, the force exerted on both of them is going to be the same. Okay. The direction of the electrical force is going to depend on the charge. So remember, like charges repel, two positives are going to move away from one another, two negatives are going to move away from one another, but then the opposite charges attract. So, electric field strength is given or measures the intensity of the force experienced by a charged particle in an electric field. And this is going to be given to us by the equation electric field strength is equal to force divided by charge, or in other words, the Coulomb's constant multiplied by the charge and then divided by the distance squared. Okay, now getting on to moving charges or our magnetic fields. So, as I said before, electrostatics concerns charges which have which exert forces on one another due to their electric fields. But now we're getting on to moving charges. So when a charge moves, it is going to generate a magnetic field. So point charges moving through an electric field have a force exerted on them according to the right-hand motor rule. And this basically just tells us that the force, the magnetic force, the direction of the field, and the velocity of the charge are all going to be perpendicular to one another. So you can just use your fingers. The strength of this force on a moving charge is going to be given by force equals QVB sine theta. Getting onto flux, strength, and production. So, magnetic substances and electromagnetics produce magnetic fields. Remember, magnetic field lines are drawn from positive to negative. So they're drawn from the north to the south. The magnetic flux is the quantity of magnetic field passing through a given area, and the magnetic field strength is the flux per unit area. So a way to think about this is if you have this square area here, and you have 4 magnetic field lines passing through it, the magnetic flux of this area might be 4, right? However, if we consider this to be, or if we wanted to find the magnetic field strength, and this was, say, 4 meters squared, then 1 meter squared per unit area is only going to have a magnetic field strength of 1 Tesla. So the magnetic flux tells us like how many lines pass through any given area at all. You know, you can have an absolutely massive area and have a lot of magnetic flux. However, with that same massive area, you could have a very small magnetic flux density, because even though it's a massive area, you know, the reason that the magnetic flux is so high is because it's a massive area, but when you actually take it per unit area, there's not actually a lot of lines passing through each unit area. And this is, of course, why the magnetic field strength is the flux per unit area. So, the magnetic flux is given by the magnetic field strength multiplied by the area, of course. And then we can determine the direction of the field given current, or vice versa, using the right hand rule. So this is shown down here. So if you get out your right hand, you can use this to tell you the electric current and the direction of the magnetic field around a current carrying wire and also around a solenoid. So we'll go over the current carrying wire one first. So when you're considering a current carrying wire, of course, the current in the wire is like moving electrons, moving charge, which is going to generate a magnetic field. So when you're considering a current carrying wire, your thumb is going to be pointing in the direction of the conventional current, not the actual current, the conventional current. Remember, conventional current is opposite to the actual current. And a lot of questions are just going to give you the current in terms of conventional current anyway, so don't worry too much about it. It's mostly just when you get into questions involving moving charges, like singular charges rather than current carrying wires. So yeah, your thumb is going to be the current, and then your fingers are going to wrap around and they're going to tell you the direction of the magnetic field. And it's going to act kind of in this circular way around the wire. Now, getting on to our application of the right-hand rule with solenoids. So, remember, a solenoid is a coil of wire, current carrying wire, wrapped in this kind of, with like this core in the center. And because we have this coil, every single section of this current carrying wire is going to be generating a little magnetic field around it. So this section is going to be like this, like this. It's going to be generating all these little like loops around each section, because that's what we've seen in this example over here. And this all accumulated together is going to generate this combined magnetic field through the center of the solenoid. So when we're using the right-hand rule with solenoids, we need to consider our fingers being the current instead of the magnetic field as they were with the current carrying wire. So our fingers are going to represent the current in the wire, and then our thumb is going to represent the direction of the magnetic field. So our thumb is going to be pointing towards north. So in this example here, our thumb is going to be pointing to the left because that's the direction of north, and because of that, we can tell which of these is the we can tell the direction of the current. So our fingers are going to be wrapping around this way, or like kind of away from you. So this tells us that the conventional current is going to be moving kind of in this direction, which makes absolute sense. Remember, because it's the conventional current, so conventional current moves from the positive to the negative. Of course, you might remember from year 11 when we went over electric circuits that electric current is generated by moving electrons, moving from the negative terminal to the positive terminal. However, that is the actual current. The conventional current is the opposite of that, as I said before. Okay. This is our syllabus link for magnetic fields. So what we need to do, or what we need to learn for magnetic fields, is we need to define a magnetic field. We need to understand representing all of the properties of magnetic fields. We need to solve problems involving magnetic fields and current carrying conductors and wires. So let's get into how we actually do that. So we can determine the magnetic field in a number of scenarios, including the magnetic field on a moving point charge, such as like a moving electron. And this is given by our first equation here. The magnetic field strength is equal to mu naught, which is the permittivity constant, and that is also in your formula sheet, divided by 4 pi, multiplied by Q, which is the charge on the point particle in coulombs, multiplied by the velocity of the charge, multiplied by the radius, the distance from the charge wire or coil, and then divided by r cubed, sorry. The magnetic field strength on a current carrying wire is going to be equal to the mu naught multiplied by the current traveling through the wire divided by 2 pi multiplied by the distance from the wire. So this is going to tell us the strength of the field at a particular point away from the wire, and our particular point is going to be our radius. It's going to tell us how far away we are from the wire. So for solenoids, um, our um, we need to find the magnetic field strength in the center um, of a solenoid, we're going to use this formula here. So we're going to have 2 pi times K, our magnetic constant, multiplied by the number of turns multiplied by the current through the solenoid divided by the length of the solenoid. Okay, now we are getting onto forces on wires and parallel conductors. So, a current carrying wire is going to generate a, um, a magnetic field, of course. However, when a wire is placed within proximity of another wire and they both um, carry current, their magnetic fields are going to interact with one another, right? Because they both can generate magnetic fields, but they're going to interact. So, if you have a look at this example here, we have these 2 wires. Remember, I'll just write this down now. Excuse me. Our notation for wires or field moving into the page and out of the page is noted by these 2 symbols. If it's out of the page, it's going to be the dot inside the circle. And if it is into the page, it's going to be the cross. The reason, or a way to remember this, is if you think about an arrow. If an arrow is flying away from you, you're going to see like the crossed kind of feathers at the back. So if an arrow is moving away from you, it's moving into the page because you see the back of it. If an arrow is moving towards you, you're going to see the tip of it, and that's going to be moving out of the page towards you. So that's just how we display if a current carrying wire or a field is going into or out of the page. So, as you can see here, our 2 wires are both carrying current into the page because I have a cross there. So their currents are moving in the same direction. So as you can see, this is going to create this massive loop of a magnetic field. And that's because if we use the right hand rule, with our thumb going into the page, at all points on either of the wires, the magnetic fields generated are going to combine, right? And because of that, if we have 2 wires traveling in the same direction, as we have here, or I should say rather with current in the same direction, they're going to be attracted to one another, right? They're going to be pulled closer to one another. However, if we have 2 wires with current moving in the opposite direction, so for this one here, it's moving into the page, and this one is moving out of the page. If we consider our right hand rule, so for our first one, it's going to be moving into the page, so our force is going to be moving around in this direction. And for our second one, our current is moving out of the page, it's going to be moving around in this direction. As you can see, the forces are going to cancel out. or rather oppose one another. Because at this point, as a result of this wire, the force wants to move in this direction. But the force as a result of the other wire wants to move in this direction. So they're going to kind of oppose one another. And as a result, when we have two wires that have currents moving in opposite directions, they're going to be repelled from one another due to the interaction of their magnetic fields. Okay, now getting on to electromagnetic induction. So, what we need to know for electromagnetic induction is all of the terms listed involving flux, electromotive force and induction, and Faraday's and Lenz's law. And then we need to solve problems involving these terms and laws. So, electromagnetic induction is the production of an electromotive force, causing electrons that are free to move to migrate to one end. As a result of this movement of electrons, a potential difference is going to be caused, or in other words, a voltage. So, as you can see, in this case, the magnet moving is going to produce a force in this coil, which is going to create a current, which we have measured with this galvanometer. So, the strength of the EMF induced depends on the rate of change of flux linkage. For the movement of wire through the field, EMF is given by the magnetic field strength multiplied by the length of the wire multiplied by the velocity that the wire is traveling at. If the wire itself is not perpendicular to the field, then we need to consider the angle at which the wire is at with the field. And this is, of course, because as the wire becomes more and more parallel to the field, it's going to be experiencing less and less of the force. So, if this is our field, and then we'll have our wire. If the wire is perpendicular to the field, then like every single point of that field is going to be like interrupting the wire, right? However, if the wire is kind of at a diagonal, then some of the field or some of the field's components are going to be missed because this wire now has components that are in the same direction as the field, meaning that they're not experiencing anything. Of course, if a wire is just like this and it's parallel with the field, then none of the lines are intercepting with it. So that's why we need to consider this sine theta. What this tells us then is that if a wire is completely parallel to a field, or in other words, if theta is 0, then there's not going to be any force induced. And that's of course because the sine of theta of 0, is equal to 0. So that's just something to remember, mostly for kind of maybe a multiple choice question. So now getting on to Lenz's law. So Lenz's law is kind of, at least what I considered in year 12 to be the like most difficult part of electromagnetism. So Lenz's law is an expression of negative feedback. What this means is that the current induced in a conductor by a changing magnetic field is in such a direction that its own induced magnetic field opposes the change that produced it. And this is kind of hard to wrap your head around. So, what this basically means is that if you induce a current using a magnetic field, then the current you induce is going to kind of like retaliate, and it's going to generate its own magnetic field in a direction that opposes your own magnetic field, right? How I kind of thought about this in year 12, just because it was kind of such a difficult concept for me, I had to think about it a lot, was that the current that I was inducing was like being a little bit petty. You know what I mean? Like, and there is actually a scientific explanation for this, which I'll get into in a second. But how I kind of thought about it was the current was being petty. Like, I was trying to generate this current using my own magnetic field, and then the current that I was generating or inducing was kind of being like, I refuse this. I refuse this magnetic field that you're introducing. It was kind of being petty. Now, the actual reason this happened is obviously not because the current is being petty. It's actually due to the law of conservation of energy. So, I'll explain this in the context of, I don't know what that word was, in the context of the solenoid, which we have here. So, here we have our solenoid, and as you can see, the magnet is moving in. When the magnet is moving into the solenoid, the current is going to be induced to oppose that motion, right? So basically, you're trying to move the magnet in, and as a result of this changing magnetic field, remember, a changing magnetic field generates EMF. A changing magnetic field induces our current. You are changing the magnetic field by moving this magnet, and as a result, the current is kind of refusing that, and it's generating its own magnetic field to oppose that. And as a result, it's going to generate a current with north in this direction so that it opposes your magnet. Now, the reason that this occurs, as I said before, is the law of conservation of energy. So think about this. If you moved your magnet into the solenoid and it induced a current that that pulled your magnet in. So you're standing there next to the solenoid, you have your magnet, and your solenoid is like pulling the magnet in, right? This doesn't make sense. Think about why this scenario doesn't make sense. Pause the lecture for a second and have a think about it. It doesn't make sense because that energy has just been like newly created, right? There is being a current that's induced, and your magnet is being pulled in. There's no resistance you're facing. It doesn't make sense. What does make sense is if you are changing the magnetic field there needs to be an opposition to that motion to generate energy to create the current. So if you're pushing a magnet in and you have to it's being opposed, you have to push in really hard. You're putting all of this energy into pushing the magnet in, and all of that energy that you're putting in, your applied force, is giving the electrons the energy to move around the solenoid. So the reason that Lenz's law occurs is because of the law of conservation of energy, right? You need to put energy into generating that current. This again occurs in the other scenario where you're moving the magnet out of the coil. So imagine you have your magnet in the coil and now you're trying to pull it out. But the coil is pulling it, trying to keep it in the center. So you're trying to pull it out, the coil is trying to keep it in the center. The reason for that is because you are changing the magnetic field, which is going to induce a current, and you are inducing a current around the coil. So if you didn't need to pull on the magnet and put energy into pulling the magnet, there wouldn't be any energy for the current to be induced. So, of course, you're pulling it out, which means that the current is going to generate a magnetic field strength that opposes that motion. Again, the current is being petty. It's saying, oh, you want to move that magnet? I don't think so. I'm going to create my own magnetic field that stops you from doing that. That's how I still think about it to this day. So because of that, the direction of the current between these two images is going to change because now it wants to keep the magnet in there. So now this end is going to be the south because the direction of the current has changed. And it's going to pull the magnet back in. Okay, so that is basically the overview of Lenz's law and how it applies. This law kind of, as I said, was really tricky for me to understand when I was in year 12, especially when you get into the application questions, and you need to apply Lenz's law to a whole different number of scenarios. So yeah, I hope that explanation really helped because it took me literally months to fully understand that. I'm not gonna lie to you guys. So by considering both Faraday's law and Lenz's law, we can derive an equation for the EMF induced in a loop with changing flux. So remember, the EMF is induced because the flux changes, the magnetic field changes. The section here about the EMF being proportional to the change in flux over the change in time is of course from Faraday's law, and then the negative out the front is of course from Lenz's law, because Lenz's law tells us the direction of induced EMF and Faraday's law tells us about the magnitude of the induced EMF. Okay, getting on to mutual induction and transformers. So this topic is pretty simple. We'll go over it kind of quickly. So a pulsing, alternating magnetic field can be induced by feeding a coil with an AC current. So this magnetic field will induce a current of the same frequency in adjacent coils. And as a result of this, if the number of coils differs, the voltage can be stepped up or down according to this formula. So recall the use of transformers is, of course, if you are transporting electricity across long distances, such as in power lines in rural areas, you need to have a high voltage because that will reduce the power loss. However, when you're actually using power or electricity in your home, you don't want that larger voltage. You only have like regular appliances. So what you want to do is you want to change the voltage. And how we do that is using our step up, step down method with our two coils. So if you have energy moving in this wire and then it is put through this coil here, and then if you have another coil here that has less turns, what's going to happen is the energy is going to travel along here, and then it is going to go through this coil here, and the movement of the charge through the coil is going to generate a magnetic field, which is thus going to impact this coil, generating a charge through this coil, which will then move off in this direction. So that's why that works. And of course, our voltage of our primary coil divided by the voltage of our secondary coil is going to be equal to the same ratio for the number of turns. So if the number of turns is different, that means that we can determine or change, step up or step down the voltage. We can do the same thing with the power. So we know that the power of the input and the power of the output always needs to be the same, because if it weren't, then we would have lost or generated energy, which doesn't adhere to the law of conservation of energy. Remember, power is given by VI, so that's why this equation exists. So the power in the primary coil is going to be equal to the power in the secondary coil. Okay, before we move on to special relativity, I just want to give you guys like a few really quick tips for studying electromagnetism. One thing I really, really, really want to emphasize is making sure that you practice complex questions for especially like electrostatics and electromagnetism, like with like magnetic fields and the current carrying wires and moving point particles and solenoids. And the reason for this is because there's always going to be a really complex question of these on an exam. And you really need to understand the interaction of multiple different components. So for electrostatics, you're going to need to understand the interaction of 3 or 4 particles and how they impact one another, how their electric fields impact one another. You're going to need to do like vector analysis involving trig. So make sure that you practice those. And then for your electromagnetism, make sure that you practice questions that involve a lot of different elements. So that could be a current carrying wire, a moving point particle, a solenoid. Make sure that it includes Lenz's law, Faraday's law, all that kind of stuff. Make sure that it involves the right hand rule, this rule here, the FBI rule. Make sure that you practice combining all of the components together. Because speaking from experience, the reason that I lost marks on my physics external was because I didn't get one of the difficult magnetism question. I think I only got half marks. So yes, that is what really bugs me. And I practiced a lot of these questions. So that's my tips. Okay, moving on to special relativity. So Um, for special relativity, we're going to delve beyond Newtonian physics and kind of onto more complicated topics. So, we're going to use special relativity concepts to describe phenomena such as muons within the atmosphere. Um, we're going to investigate the consequences of light's constant speed, such as time dilation and length contraction. We're going to investigate the energy-mass equivalence relationship. And then we're going to use special relativity to explain why nothing can travel faster than light and kind of paradoxical scenarios such as the flashlight on a train paradox. In my opinion, special relativity is like the coolest topic for Year 12 physics. It's just like really interesting and like really, really wacky at first, but it's actually like, it's really interesting. I really enjoyed learning it. And I mean, I couldn't say the same about some of the other elements of physics. Not that I didn't enjoy them, but like, they were kind of like, oh yeah, like projectile motion, but special relativity is like cool. Okay, I'm excited. Okay, so time dilation is the difference in elapsed time measured by two clocks, either due to them having a relative velocity to one another or gravitational potential difference between them. So this is what we can see here. In this scenario, frame A and frame B, the clocks are measuring different times. So length contraction is the phenomenon wherein a moving object's length is measured to be shorter than its length when at rest, and when the length of the object decreases in the same direction that it travels. So these are kind of like two symptoms of an issue that we'll get into. The first one being that if an object is moving relative to another one, then the time that it experiences is going to be different. So if an object is moving faster relative to another, then it's going to experience time more slowly. And I say these words with caution because it's kind of a fickle subject to word. What I mean by that is if you're moving faster relative to somebody else, so say you travel in a spaceship to really, really far away, you have traveled faster relative to somebody who isn't on a spaceship, right? Say Jeff, you're traveling faster than Jeff. Jeff is going to experience more time than you, right? And as a result, Jeff is going to age more than you do because you're moving faster relative to him. That doesn't mean that you yourself experience time more slowly. It's not like everything is in slow motion for you. You experience time normally, how like you normally would. Same thing with Jeff. He experiences time like he normally would. But because you guys have this relative motion, your elapsed time is going to be different. This also isn't to say that one of you has like a correct perception of time, right? You can't say, well, obviously Jeff's perception of time is correct because he wasn't moving, but you were. That is not what's happening. You and Jeff moved relative to one another, right? For all you know, and this may sound silly at first, for all you know, you were in the spaceship staying still, and Jeff just kind of like catapulted away from you, right? Because that's your perception. No one perception is wrong. There's no like right amount of time to be experienced. It's all just relative, which is just so cool. And we'll get into the actual reason that this happens, this time dilation happens in a little bit, if you're wondering why. But that's just the basic concept behind it. A similar thing occurs with length contraction. So length contraction occurs when a moving object's length is measured to be shorter than its length when at rest. So if, for example, you are standing on the side of the road and a very, 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 very fast car, a car that could never exist because it goes so fast, drives past you. When you look at that car, you are going to see the car as kind of squished up in its direction of motion because it's traveling so fast. So its length has contracted in the direction that it's traveling in. It hasn't gotten shorter, like it hasn't gotten like a little flat pancake car, but it has gotten like squished up in the direction that it's traveling in. When you see the car normally not at rest, not in motion with respect to yourself. If you see, you're just standing next to the car with your hand on it kind of thing, it's going to be way longer than you experience it when it's traveling at such a fast speeds past you. Similarly, if you are the driver of that car and you are driving down the road really, really, really fast, you're going to experience everything outside of you as kind of skinnier in the direction of travel, right? That's also going to be squished up because from your perspective, the relative motion is the world around you. So all the houses you're going to see are going to be like all skinny, and everything like that is going to be all kind of contracted in the direction of motion. That isn't to say that everything is going to kind of like get taller. It just means that the everything is going to contract in the direction of motion. Same thing here. No one's person perception is correct, right? So your perception, whether you're in the car or whether you're outside, isn't correct or incorrect. It's just the things that you perceive due to you being in that, having that motion with respect to the other party. Okay. Moving on from this slide, we are now going to get onto energy mass equivalence. So this one is pretty simple. It just tells us that anything with mass has an equivalent amount of energy and vice versa. E equals mc squared. Pretty famous. So this just tells us that mass and energy are convertible. We'll get into applications of this formula involving how mass changes when an object moves at speeds. But we don't need to know much more about it at this moment. Okay. Getting onto the speed of light in relation to special relativity. So, we know that the speed of light in a vacuum is the universal speed limit, right? But why? So we know that nothing can travel faster than light. You may have heard that before. We know that this is the universal speed limit because as an object approaches the speed of light, as it gets faster and faster, its mass approaches infinity and the elapsed time approaches zero. What this means is that time stops altogether at the speed of light. So, this sounds like absolutely crazy when you first hear it, right? Like, how is this mass increasing as it approaches the speed of light? How is time not going to exist, right? So, what I firstly want to talk about with respect to the mass approaching infinity is that as you accelerate an object, if you're accelerating an object to such great speeds that it is approaching the speed of light, what actually happens is that you kind of have a law of diminishing returns situation. So, what happens is as you are putting more and more energy into accelerating this object, as it's getting closer and closer to the speed of light, the energy that you put into accelerating it actually, at an increasing rate, stops going towards accelerating the object and actually starts contributing to its mass, which sounds crazy at first. And it also sounds partially crazy because we've only done a very, very fast overview of this topic. But as you are putting more and more energy into this object, the energy that you're putting in is actually increasing its mass and therefore not accelerating it. So it's accelerating less and less, and the mass is increasing more and more. And as a result of this, if the mass is so great, the force that you're applying will cause it not to accelerate, right? Because if you have an infinite mass, no amount of force will be able to move it. And in other words, the object cannot exceed the speed of light. The other reason that the object cannot reach the speed of light is because time stops altogether. So remember what we were talking about before in the previous slides about how if an object is kind of moving a lot faster relative to you, it's going to experience time more slowly than you do. This result is exacerbated as you get closer and closer to the speed of light. This is why we don't notice it kind of in everyday life, because we are not going anywhere near the speed that we would need to be, right? But if an object is actually moving a lot closer to the speed of light, the effect is going to be way more noticeable. As you get closer and closer to the speed of light, the time is going to slow down more and more, right? As an object gets like right next to the speed of light, time is basically stopped in comparison to somebody who's stationary relative to them. So at the speed of light, we can kind of deduce that time is zero, or like time doesn't exist. So this kind of like sounds very crazy if you it sounds very crazy, like, probably because you guys haven't started on special relativity yet. Um, but I just kind of want to say one more thing before we move on to quantum. Um, and that's kind of like a basic explanation of why this all happens. So, the reason that all of these strange things are happening with our time dilation and our length contraction, and like the fact that nothing can move at the speed of light, or no object can with mass can move at the speed of light. The only thing that can move at the speed of light is, waves, things without mass. Um, the reason this all occurs is because Einstein, who came up with this theory, observed that the speed of light is constant. The speed of light never changes. So regardless of how you are moving, as long as you're moving with a constant velocity, the speed of light in a vacuum is always going to be the same. So if you are standing, or rather sitting still at your desk right now, you're going to see light traveling at the same speed as you would if you were in a train moving really, really fast, or in a spaceship moving really, really fast. You would still see light as traveling at the same speed. So, what this means is that basically, if you are traveling in your spaceship, say this is your spaceship here, listen, I know that this is a terrible spaceship. Say this is your spaceship here. If you are traveling really fast, but you still perceive light as traveling at the same speed, your time kind of needs to slow down to make up for that, right? Because you're still seeing light travel at the same speed as somebody who is standing outside of your spaceship, and is not moving, right? Somebody who's standing outside of your spaceship still sees light travel at the same speed, right? Which means that kind of your actual perceptions of time need to make up for that. So if you're traveling really, really fast, your speed is kind of almost comparable to that of light. And this is when you see the greatest effect. If your speed is almost comparable to that of light, but yet somebody standing on the side of the road still sees light traveling at the same speed, your experience of time needs to compensate for that because you're traveling so fast. Okay, hopefully that is a detailed enough overview for you guys. I know personally I find all this stuff really cool. But now we're going to get on to quantum theory. So, quantum theory is also pretty cool. It tells us about the wave model of light, and then a lot about the model of the different models of the atom, and the photoelectric effect, which is also really cool. So, when we're working with quantum theory, we get into a number of different topics, which firstly involve Young's double slit experiment. You may have heard of that already, just kind of as general knowledge, and the wave model of light. So the tricky thing with Young's double slit experiment and the black body radiation. These two differing experiments done kind of in the late 1800s and early 1900s, which which kind of provide evidence both that light can act as a wave, but light can also act as just a discrete particle. So, basically, we have evidence from Young's double slit experiment that light is wave, but we have evidence from black body radiation and also from the photoelectric effect, which was another experiment done even later than that in the 1900s, which show that light is a particle. So Einstein basically came up with this theory, which describes light as being both a wave and a particle. So we're then going to investigate the dual wave particle nature of electromagnetic radiation. We're then going to solve problems involving the photoelectric effect, and then describe the Bohr and Rutherford model of the atom, and how it integrates light quanta and atomic energy states to explain wavelengths observed in the hydrogen emission spectra. So, getting into Young's experiment. So, Young's double slit experiment was performed in the early 19th century by Thomas Young, and it helped to prove the wave model of light. So, how it did that is it showed the presence of interference patterns, proving that light acts as a wave. So, what Young observed was that if he kind of had a piece of screen with two slits and he shone light through the screen, he would see a destructive and constructive interference pattern, which basically you would have learnt about previously in year 11 with waves, which is where like the two positive parts of a wave will collide and create an even bigger positive part, or the two negative parts will collide, or alternatively two kind of opposing parts, either a positive displacement and negative displacement will collide to kind of cancel out. So this is kind of, I'll draw actually more of a diagram because it'll be more helpful to what he saw. So basically what he saw, the pattern that he saw was kind of a big pattern of light, two big patterns of light with kind of petering out sections on either side, which describes like an interference pattern of waves. As we can see in the next slide, what he would have seen if light acted solely as a particle was this like evenly distributed patches of particles. So in this experiment, we're just seeing electrons, which are obviously particles. So what he saw with light was these kind of like this uneven pattern where we have all of these different like splotches of light, which kind of implies that when the light goes through the slits, it bends around the slit and creates these patterns. However, if light was a particle, the particles would have just gone through these two slits and created like two big splotches of particles right on either sides of the splits. So this is how he knew that light could act as a wave. Okay, now we are getting onto the Bohr model. So the Bohr model of the atom is probably the one that you guys are most familiar with. It's a model of the atom where negative electrons orbit in discrete energy levels around a positively charged nucleus. So we have the protons and the neutrons in the nucleus, and then the electrons orbiting around. An important feature of the Bohr model is that the electrons can only exist in discrete energy states. So the electrons are going to have a certain amount of kinetic energy, and the orbital ring that the electron is going to be in depends on that energy. So if it has more energy, then it's going to be closer to the outside of the atom, but if it has less energy, then it's going to be closer to the inside. However, an electron cannot be in between energy states, right? It can never be on 1.5. It can either be on one or the other. It can never be in between. Okay. Photons incident on atoms can cause electrons to go up in energy levels into causing anti-bonding orbitals. So what this means is that if a photon, which is a particle of light, interacts with an atom, it's going to give the atom all of its energy. And as a result, some of the electrons are thus going to have all this extra energy and jump out of the atom. When the electrons fall back down to lower energy levels closer to the nucleus, then a photon of equal energy is going to be emitted. This model proves that light can also act in discrete quantity, photons. The energy of the photon is going to match the difference in between energy of the orbitals. And we can calculate the energy using Planck's equation, which is what we have here. Change in energy is going to be h multiplied by the frequency. Where h, is Planck's constant. Okay. Getting really quickly onto the Standard Model. So, for the Standard Model, we need to define the concept of elementary particles and antiparticles. We're going to go over a lot of different types of particles and forces, and then go over the interactions between these particles. So, in our investigations of the Standard Model, we're going to define elementary particles and antiparticles. We're going to recall the 6 quarks, baryons and mesons, the 6 leptons, and the 4 gauge bosons. There's just like a lot of different particles to remember, basically. We're going to describe the 4 different forces, the strong nuclear, weak nuclear, electromagnetic forces, and how they influence gauge bosons. The other one is the force of gravity, but we don't go into it with the Standard Model because it's not as relevant. It's very weak. It's a very weak force. Sorry, gravity, you're very weak. Then we're also going to investigate particle interactions, including the conservation of lepton and baryon numbers. And then we're going to investigate electron and electron interactions and electron and positron interactions, and then neutron and proton decay using Feynman diagrams. So, This massive table tells us about the standard model of elementary particles. Listen, I'm not going to go through all of these today just because it would be like telling you guys a big long list of names that you are never going to remember and is not going to be helpful to you. But essentially what we have is our quarks, which are the tiny, tiny particles that make up our protons and neutrons and other such particles. So these are like, if you think about the nucleus and the protons and neutrons, the quarks are the tiny particles even inside those. Oh, just banged on my table. Got so excited about the nucleus. And each of these quarks has their own like anti-quarks, right? They're like the opposite of those. We also then have our leptons, and leptons are like our separate particles. So they don't make up neutrons and protons. Our leptons are things like electrons and muons. So they're kind of separate particles. And then, of course, we're going to have our corresponding antiparticles for each of these. And all of our antiparticles are going to have the same mass, but the opposite charge of all of our original particles. And then we also have our four force carriers, or our gauge bosons, and these carry our forces. So the one you might be most familiar with is the photon, which is the gauge boson for light. So basically saying light is that right? I don't think so. So I think I just told you guys the wrong information. Maybe it is. I'm actually not quite too sure. But basically these particles carry our four forces. Okay, getting onto the interactions of, no, sorry, I was right. Electromagnetic interaction is a photon. I don't know what I'm thinking. I'm very tired. So our gauge bosons are the force carriers. So they carry the forces between our other particles. So weak nuclear force and electromagnetic, and then the strong nuclear force is our gluons. We're going to delve deeper into the fundamental interactions that cause these forces, as well as investigate the standard model and particle interactions further later in year 12. So the Feynman diagrams describe what happens when elementary particles collide, and you can see a few of these over here. Okay, that is it for our content for today. In the next few minutes, I'm just going to go over some of the tips that I have for you guys, some for getting through year 12, some of the study tips that I have for you guys. Again, if you have any questions about study tips, please feel free to ask them in the chat. What I want to recommend firstly is make sure you're doing practice questions in exam conditions. Make sure you have your formula sheets so you learn where all the formulas are. You're using your graphics calculator. You can time them as well. But essentially means just to make sure you're not constantly looking back at your notes and that you are remembering everything. Something I will also recommend when you're practicing questions is to make sure that you're practicing like difficult enough questions. Make sure you extend yourself. It's really easy to kind of like practice the easy questions and then like kind of not go any further than that and not practice any of the harder questions. You really need to practice the harder questions, especially for electromagnetism, because of course there are going to be complex unfamiliar questions on the external. They do always try to trick you up, even with the simple familiar questions, they're going to try to trick you up. So make sure that you practice like harder questions once you get to it. Make sure you extend to that. The other thing is spaced retrieval. So make sure that within certain intervals you are remembering the content, like practicing to remember the content. So immediately after you learn it, that afternoon, a few days later, a week later, so on. Make sure you're not looking back at your notes. You just ask yourself, okay, what is EMF? What is Lenz's law? How do you solve a problem using Lenz's law? Stuff like that without looking back at your notes, and do it in certain intervals after learning it. Another thing that I'd recommend in terms of like remembering the content, other than practicing questions, but actually remembering the content, the definitions and stuff like that, is, as I said before, make sure you copy down the QCEE definitions and remember those specifically. And also when you're learning, when you're practicing for like the syllabus dot points for like explain, describe, where you're kind of explaining or describing a concept, what I did and what really helped me is to write up a really, really concise explanation of the concept in my own words and then memorize that. The reason that I'd recommend this is because in your exam, you're always going to get a few questions that are like, explain this concept. And all you need to do in that question is just copy down your memorized answer. If you've just memorized an answer, you're making sure that A, you're not going to miss any info when you're writing in your exam. And B, you're not wasting time in your exam thinking of the answer. You're just going to copy it down and it's going to be done, and then you have time for the other questions. Okay. Make sure to mark all of your work. Of course, if you're getting questions wrong, the practice doesn't really count. Make sure you create a log of the mistakes that you make. This is really, really important, especially if you make like some really concise notes for your external with all the concepts on them. If for each topic you make a list of mistakes that you typically tend to make, this is really, really helpful. Make sure you keep some variety in your notes. Add from multiple sources, different textbooks if you don't understand anything, different images, anything like that. But keep it focused. What I typically tended to do in year 12 was I would have notes, my class notes, where I'd like type down everything that my teacher said, all my practice questions, all of that. But I would then transfer that to my super concise external notes. And in that, I would only have exactly what I needed. And all of my notes would correspond to all the syllabus dot points, so I knew I didn't miss anything. Okay. Another tip is to make sure that you take mocks seriously, and then keep a glossary definition bank using the QCEE definitions. And make sure you start practicing them now as well. You have a lot of definitions to remember. And then still some friends, make a study group, have fun with it, do things together. Otherwise, it just kind of isn't as much of a good time. Make sure that you're kind of looking forward to studying, and that you're not kind of dreading it. It will really help in making sure that you stay motivated. Another tip for that as well, to make sure you're enjoying studying, is to kind of like maybe like listen to some really good music. Sounds like so like a lot of people say that, but it does actually help. If I put on a good long playlist of Taylor Swift, um, it honestly doesn't even matter if I don't like the work, I'm just vibing. Okay. Um, and yeah, thank you so much for having me today, guys. I've really enjoyed um, going over all of the content with you guys. A lot of this content is really fun to like learn and explain for me. I hope that all of the study tips have really helped you. I hope you're feeling like a little bit more comfortable continuing on with year 12. Um, and yeah, good luck with your externals. Good luck with your assignments. And I hope that you have a great rest of your day. See you guys.